If you've ever measured something, you probably realize it can be surprisingly tricky. For example, if you're measuring your height, you might take 5 measurements and get 5 slightly different answers. And even when we're not in the measurement game ourselves, we're relying on other people's measurements to make decisions, and those are going to have some of the same problems. At the end of the day, if we're going to make rational decisions, we need to be able to trust that our measurements reflect what's actually happening in the world. We need to be able to tell apart the different ways we might potentially get things wrong and come up with ways to deal with it. One way that our data, our collection of measurements, can be uncertain is that they are scattered. When your measurements are all over the place, it can be hard to tell what the answer is. Maybe the measurement you're trying to make is just really difficult, like trying to measure your own height with a tape measure. You try, and each time it comes out a little different. This situation, when your measurements vary a lot, is called statistical uncertainty. With statistical uncertainty, even though your measurements might be scattered, you can take an average and get a good answer about what's really going on out there in the world. Better measurements will average down faster because each one is closer to the truth, but no matter how messy your data is, the average will get you an answer that tells you something reliable about the world, as long as the mess is just due to random scatter. Now, there's also a second type of uncertainty, which happens when your measurements are biased in some consistent way, not randomly scattered. Maybe the equipment or measurement process is pushing your measurements in one direction away from the correct answer. If this is the case, no matter how many times you measure something, you'll still get the wrong result, even if you take the average. This would be like if you were trying to measure your height, but your tape measure had been shrunk in the wash, let's say. This type of uncertainty is called systematic uncertainty. These two types of uncertainty are such a common part of measuring things that most branches of science have words to describe them. For example, in statistics, people use the word precision to describe how much statistical uncertainty is in data, and they use the word accuracy to describe how much systematic uncertainty there is. But we'll just stick with the physics terms for now. I was trying to think of examples to show these two types of uncertainty so that they're crisp in your mind whenever you need them. One that came to mind was checking your weight every day on a long cross-continental trip. In every hotel room, you pull out the bathroom scale and weigh yourself. The first time, the scale reads 3 kilograms, less than what you thought your real weight is. Then you travel to the next town and you try their bathroom scale, and you get a measurement that says you are, say, 2 kilograms heavier than you think you are. Over a whole month of traveling, you try lots of scales and get different answers. In this case, you'd be dealing with statistical uncertainty because your measurements are really scattered, but they are varying randomly. An important thing to remember about statistical uncertainty is that it can come from measurement error, but it can also happen because things you're measuring vary naturally. Some of that variation might not just be because the scales are off. Maybe during your trip you lost or gained a little weight or got a haircut. That natural variation is all part of statistical uncertainty too. Now, to look at a different situation, imagine your scale at home was biased. Suppose it read 3 kilograms lighter than your real weight. If you never checked it against another scale, you could go through life never knowing your true weight. In this case, you'd be dealing with systematic uncertainty. The instrument, your scale, would be creating false bias in your measurements. Of course, this is exactly the kind of thing that scientists are constantly trying to check for. You want to know if you're in a situation where you're getting a nice, consistent, repeatable result, but that also happens to be wrong. These are such common issues that people over the years have thought a lot about how to deal with each of them. For statistical uncertainty, there are a couple of things to try. You can either try to take better measurements that have less scatter around the correct answer, or you can take many, many more measurements and average them out. But when you have a systematic uncertainty, that's your chance to be creative. You start by trying to figure out what systematic errors you might be missing. It's a big job to try to guess what could be causing systematic bias because there are so many possibilities. In fact, a huge amount of what scientists study in their training is just getting better and better at thinking of ways to find systematic uncertainty and also to deal with it. The good news is that there are lots of things you can do to trust your data, even if you think there is systematic uncertainty. First, it might not matter so much if your measurements are biased if they're biased in a consistent way. For example, if you want to check that the heat in your house is working, it doesn't actually matter if your thermometer is always reading 10 degrees too cold. What you're looking for is an increase in temperature when you turn on the furnace. In these situations, you can compare measurements to each other when the actual numbers don't matter so much. Another way to deal with bias is to understand the size of the effect and try to correct for it. So if you do some tests and you know that your thermometer always reads 10 degrees too cold, you can just go back and add 10 degrees to all your measurements. Here's a real-life example that I recently worked on with some climate researchers, where we had to deal with both statistical and systematic uncertainty. During the past century, amateur meteorologists all over the world kept track of their local temperatures by checking their thermometers every day. Climate scientists have used those measurements to estimate the change in average global temperature. But in order to be sure about any temperature changes, we needed to look into both types of uncertainty. Of course, in a big project like this, there is going to be lots of statistical uncertainty. Plenty of people over the years have read a thermometer a little wrong or just happened to be collecting measurements during a time when temperature varied a lot. But to identify possible sources of systematic uncertainty, you need to consider all the ways people made temperature measurements all over the world and then find out whether those changed from the beginning to the end of the century. We looked at lots of different ways that the measurement process might have changed and caused systematic uncertainty. For example, over the last century, the amateur meteorologist groups changed the guidelines about what time of day to collect measurements. You can imagine that if everyone was checking the temperature at 6 in the morning, and then later they switched to checking at noon, that might really change the results. We had to factor in how much the change in timing might have affected the data. In order to really trust our results on global temperatures, we had to check for dozens of other sources of systematic uncertainty too. This is all really meant to be a starting point, to get you thinking about how those two types of uncertainty show up in all the measurements in the world. At the end of the day, all our measurements and data are going to be imperfect, but we still need to use them to make important decisions. The really great thing is that if you can establish that the amount of uncertainty is small enough and that any systematic biases are controllable, then you can use your data to better understand the world and to make those important decisions that rely on the measurements. If you really know your uncertainties, you can even bet your life on the data.